In mathematics, an implicit equation is a relation of the form r, x1, xn, equals 0, where r is a function of several variables. For example, the implicit equation of the unit circle is, an implicit function is a function that is defined implicitly by an implicit equation, by associating one of the variables with the others. Thus, an implicit function for y in the context of the unit circle is defined implicitly by. This implicit equation defines f as a function of x only if -1 a per mil currency x a per mil 1 currency and 1 considers only non-negative values for the values of the function. The implicit function theorem provides conditions under which a relation defines an implicit function. Examples: inverse functions equals, a common type of implicit function is an inverse function. If f is a function of x, then the inverse function of f, called fa1, is the function giving a solution of the equation. For x in terms of y, this solution is. Intuitively, an inverse function is obtained from f by interchanging the roles of the dependent and independent variables. Stated another way, the inverse function gives the solution for x of the equation. Example: the product log is an implicit function giving the solution for x of the equation y(x(x) equals 0. Algebraic functions equals. An algebraic function is a function that satisfies a polynomial equation whose coefficients are themselves polynomials. For example, an algebraic function in one variable x gives a solution for y of an equation where the coefficients I, x, are polynomial functions of x. Algebraic functions play an important role in mathematical analysis and algebraic geometry. A simple example of an algebraic function is given by the left side of the unit circle equation. Solving for y gives an explicit solution. But even without specifying this explicit solution, it is possible to refer to the implicit solution of the unit circle equation. While explicit solutions can be found for equations that are quadratic, cubic, and quartic in y, the same is not in general true for quintic and higher degree equations, such as. Nevertheless, one can still refer to the implicit solution y equals g, x, involving the multi-valued implicit function g. Caveats: not every equation r, x, y, equals 0 implies a graph of a single-valued function, the circle equation being one prominent example. Another example is an implicit function given by x as c, y, equals 0 where c is a cubic polynomial having a hump in its graph. Thus, for an implicit function to be a true function it might be necessary to use just part of the graph. An implicit function can sometimes be successfully defined as a true function only after zooming in on some part of the x-axis and cutting away some unwanted function branches. Then an equation expressing y as an implicit function of the other variable, s, can be written. The defining equation r, x, y, equals 0 can also have other pathologies. For example, the equation x equals 0 does not imply a function f, x, giving solutions for y at all. It is a vertical line. In order to avoid a problem like this, various constraints are frequently imposed on the allowable sorts of equations or on the domain. The implicit function theorem provides a uniform way of handling these sorts of pathologies. Implicit differentiation: in calculus, a method called implicit differentiation makes use of the chain rule to differentiate implicitly defined functions. For differentiating an implicit function y, x, defined by an equation r, x, y, equals 0, it is not generally possible to solve it explicitly for y and then differentiate. Instead, one can differentiate r, x, y, with respect to x and y and then solve a linear equation in dy/dx forgetting explicitly the derivative in terms of x and y. Even when it is possible to solve explicitly the equation, the resulting formula is, in general, much simpler and easier to use. Examples 1. Consider for example. This equation is easy to solve for y, giving where the right side is the explicit form of the function y, x. Differentiation then gives dy dx equals 1. Alternatively, one can totally differentiate the original equation, Solving for dy dx gives the same answer as obtained previously. 2. An example of an implicit function, for which implicit differentiation is easier than using explicit differentiation, the function y, x, defined by the equation. For differentiating this explicitly with respect to x, one has first to get and then differentiate this function. This creates two derivatives, one for y greater than 0 and another for y